Into that natural wall integration. Did you show that? I did like the first two on like the second part, and I was like, nah.
Yeah, that was.
I was like, I'm done. I just did not want to do that. That was the hard.
Did y'all understand how to do the homework?
What?
The homework?
This homework?
Yeah.
Snapchat did.
Like these?
Like the last, like what, 2, 3?
Last two.
Yeah.
I don't know what the difference.
I remember doing this.
Differentiation.
Oh, implicit differentiation. That's like when you do the you have y in your thing, right? So then instead of using like dy dx, it's like I don't know. You do the one thing and the derivative's like flipped. So then you're finding like the derivative of y, and then like somehow you put that back in. I remember doing it. I don't know how to do it.
You do the one.
Yeah, you do the one thing and then you put the thing in. That's all I got. Because when we did that lesson, I think we were still on videos. Instead of the live streams.
So you know a little bit.
Huh?
So you know a little bit.
Just the teensy a little bit. It rings the bell. Dude, this is a pre-COVID pencil. Pencil was around. Pencil was around before COVID
I'm
was.
pretty sure this is yours too.
Yo.
Because you used to give me so many pencils.
Yeah, like you could do that in the fourth period. Yeah, exactly. It was great. It was a good. It was a good system. I mean, it worked good for me. It didn't really do much for you. Yeah. Whoa. What's going on over there, Todd? I believe what I want.
No,
I don't know if that's working or not.
He just started working with the bases, and I was literally so tired. I fell asleep.
Graph mistake of
Like that one time we came. Yeah, but look,
It's
it's not like it's the x plus 4 x plus 1.
He was like, okay, run it again.
Say it to be honest. It was like that day we.
It's not too dramatically.
It was like that day we came in and there was like 3 triangles on the board. And I was like, I like what I'm seeing.
I can't even stop the taking,
It
man.
was like, you should put that in there. And I was like, oh, I know that one.
Marching drums?
Ocean.
You gotta keep me on today. I will, right? Whenever you see me drifting off, smack it.
Why does it say my tail?
This is the only time you'll ever be able to smack me.
The time change, it was like yesterday.
It says my tail. Yeah. That's not good. I didn't even realize. Because mine told me it successfully submitted when I was at. Yeah, okay. Okay, it says it right here, so I have a screenshot of that.
That's good.
What difference is it? No, there's no. This is not submitted, I'm thinking. Why is it? I'm at when I turned it in. So.
All right, guys.
My,
How's everybody doing? Enjoy our nice weekend.
Yes, sir.
Good. Got some homework to show me, I believe. Oh, goodness. Let's walk this down.
Today. Unless it's here, I can't do it right now, but it's in the.
It's a demo. I did like the project or whatever. It was.
This solution for your own campus.
I didn't even know.
I suppose the answer to your question is no, I don't have it.
That is important.
It is. You should probably go ahead and submit that then.
Yeah, well, I didn't take pictures of it. I scanned it with my phone, and I don't have the test book in here.
I got copies. I got copies. We didn't get a chance to get into those ones at the end of class. But they're not anything exceedingly, strict. You just have to remember what the total implicit differentiation is.
Okay. Well, let's get this party started. Any homework questions for 5-1 we'd like to talk about, we'd like to go over or go through?
Seven.
73. Mr. Carlson? Sorry, did you say 83? Yeah.
59.
59. Bring our answer key up here for us, so you can see and work through each of these together. That's not 2. That's not going to help us. All right, so we're going to go to did you say 59? Did I mishear you? This 59 was not an assigned problem. Was it? We'll take a look at it anyway. It's on my answer key. I guess I just skipped it. What was the other one? Yeah, 73, 80. Okay. Well, we got those two right there. So let's start with 59. And we'll go ahead. We'll talk 73 and 83. So let's go ahead and let's talk 59 first. 59 would be 59. We have the natural log of t over t squared. The natural log of t over t squared. So we want to do a derivative here, yes? Okay, so how do you guys want to start this? What jumps out to you guys right away? No? Okay, we can try a quotient rule. Let's see how it goes. See how it goes. So we'll have f and g, right? So the derivative of f would be what here? Derivative of natural log t would just be 1 over t times the derivative of what's inside, which is also just 1 here, right? So that's a pretty easy derivative, 1 over t. And derivative of g would be 2t, yes? Okay, well, let's set up our quotient rule. Quotient rule traditionally, g squared, g f derivative, f g derivative. Okay, so let's bring everything in as we have it. So we have g, which is t squared, times f's derivative, which is 1 over t, minus f, which is the natural log of t, times g's derivative, which is 2t, all over g squared, which would be t to the 4th power. Are we all okay with this so far? Okay, let's do a little simplifying here. This is going to become t minus natural log, or 2t, natural log t all over t to the 4th. I'm going to factor a GCF out of a t here. The numerator, so that's going to give me 1 minus 2 natural log t all over t to the 4th power. I can go ahead and cancel this now. And look at a 1 minus the 2 natural log t all over t cubed, or 1 minus natural log t squared over t cubed. If I bring that 2 up. Questions here? I think this is a good stopping point for this problem. Generally speaking, I'd go with the one on the far right, though there is nothing wrong with this format either. Either one of these would be acceptable, I think, to me for a good finish point. Questions? Okay, let's take a look at 83 and 73. Let's take a look at 83 and 73. Let's take a look at 73. 73, same section here. We're looking at the natural log of -1 plus sine x over 2 plus sine x. And this is our absolute value. Okay, so what do we want to do here? We could try to do the derivative outright from this point. We could. The problem here being is that it's going to get relatively ugly relatively quickly. The first thing that we would have to do is we would have to do the inverse of this, which would be 2 plus sine x is going to move to the top, -1 plus sine x to the bottom. That's not really the issue there. The issue comes from the secondary part, which is going to be doing the quotient rule of what's inside. That's going to be, it's not impossible to do. It's just going to be very, very, very unfriendly to do. You could go about it in this manner. There is, however, an easier way to do this. Make sure I copy my problem down correctly. Okay, so let's look at what I have up here. First thing I would do is unstack this log. I would unstack this log. I'm going to use my quotient rule for logarithms to create two individual ones. Because this fraction isn't helping me the way it is, it's not going to help me the way it is. I don't have that 1 over u and then du kind of, I can't do a quick u substitution on this is what I'm trying to drive at, right? There's no quick, easy u substitution here for this. So because that's not going to help me, let's unstack the logs. Natural log 1 or -1 plus sine x minus natural log 2 plus sine x. And of course, these are still absolute values. Are we okay with the first step that I've done there? Okay, next thing is what I'm going to do is I'm going to do the derivative of each of these individually. So the derivative of this is going to be 1 over -1 plus sine x times the derivative of what's inside. What's inside is going to be cosine x minus 1 over 2 sine x. Once again, times derivative of cosine x. Are we all okay with that so far? Okay, let's just simplify it down. Put the cosine x on top. Cosine x over sine x minus 1. I'm going to just rewrite that so that way it makes more sense. And cosine x over 2 plus sine x. And that's what we have there on my answer key right there. Now, alternatively, you can put these two together. You can make a common denominator and make it into one giant cohesive fraction, which is what I have on the other side on my answer key there. Yeah, had we gone with the what I started there in green, and this is what we talked about on Thursday, where I started by flipping this, and then I start the quotient rule. This in green would lead me to that answer on the right, that 3 cosine x, a lot faster than putting this together will. So it's kind of about the way you approach the problem. It's kind of about the way you approach the problem. Once again, there's really nothing wrong with doing the quotient rule other than that quotient rule is going to take you a little bit longer to do. I think that this is a much faster and easier way to attack this problem than going through this method up here in green. You could. You have all the skill set you need, but I'm all about the easiest way to do the problem, and I think that this way is easy. Questions? Okay. 83 then. Let's take a look at 83. Take a look at 83, where is it? Oh, using implicit differentiation. So we didn't get a chance to talk about these ones at the end of class last week, but they're not anything super ridiculously hard for us to wrap our minds around if we just remember what implicit differentiation is in the first place. Okay, so what is the goal of implicit differentiation? What do we want to do? What's the steps we have to take? Go.
Don't you take the derivative of everything and then solve for dy dx?
Absolutely. We're going to set up and just going to do the derivative of each term, right? And then when we get to the derivative of doing y, we'll just write the derivative of y as dy dx. And then the second phase of the problem is to isolate those dy dx's alone on one side, correct? Okay, so I'm just going to go ahead and start by doing the derivative here. So the first derivative here is this is going to be 3x squared, right? I'm going to treat this 3 like a multiplier. So this is going to become -3 times the derivative of the natural log of y would be 1 over y, correct? Times the derivative of what's inside, which is y. So the derivative of that would be dy dx. Is everybody okay so far? Okay. Derivative of our third term here, that's going to become 2y times the derivative of y, which would once again be dy dx. All equal to derivative of 10 is 0. Are we okay with what we've done to start? Okay. Now we just need to isolate. Yes, Brian.
Isn't it x squared?
Did I copy the problem down wrong? 83. Oh, yeah, it is. Thanks, Brian. It should be. That's one too many powers there. Okay, so that's x squared. So that makes this 2x. Good catch, Ryan. Good catch. Not going to make a big difference in the problem, but still, we need to get it right. Okay, so now we're just going to isolate dy dx. So everything else is going to go to the other side. So I'm going to move this 2x over first. Move that 2x over first. I'm going to have this as -3y dy dx minus 2y dy dx equal to -2x. So everybody okay with this step? I'm going to GCF a dy dx out. And I have -3 minus 2y. That looks terrible. Let's try to write more neatly here. 2y equal to -2x. And now let's just divide this over. We got dy dx equal to, this is going to be -2x over -3y minus 2y. Questions here? Concerns here? Now, there's a couple more steps I can take here. The first thing that stands out to me, of course, is I can put this denominator together. I could put this denominator together and make this into -2x over, that's going to be -2y squared minus 3 all over y. I could do it like that. I could unstack that and make that -2xy over -2y squared minus 3. And I could take a negative from everything and make that positive 2xy over 2y squared minus 3 equal to dy dx. So from that point forward, it's just a little bit of algebra, just reducing things down. I didn't go that full way here. I think I have a little bit of a sign error going on in my Andes key, but that's not a big deal. Questions here or concerns here about this particular problem? Okay. In all reality, I could have taught you to do the derivative of natural log. I could have taught you all of 5.1 back when we first started doing derivatives in Unit 2. Honestly, I could have slipped that rule in there with the rest of them. I could have. But I just think that it works better to do it as its own lead into our own unit here rather than trying to overwhelm you as you're already learning derivatives. One less rule, I think, works a little bit easier. Plus, these work better. Doing the derivative of the natural log work better. I think once you have a better command and better practice and a better foundation of derivatives in the first place. Okay, so let's go ahead. Let's talk about what we're going to do today. So, previous lesson, we talked about doing the derivative of natural logs. Today, we're going to do the integrals of natural logs, which are a little bit more complicated. Not by much, but a little bit. I guess it's a little bit different. It's a little funky. Okay? So, slide 2 has our homework, page 340. What we're looking at there. Okay? And copy that down at your own pace. Let's go ahead on to slide 3. So these are the basic rules for integration for us to get a natural log. So this is its primary use, is for us to deal with things that we previously could not use the power rule for. The ones that we're going to focus on the most is actually number 3 up there. The one we're going to focus on the most is number 3 up there. 1 and 2 are pretty much the exact same rule, just showing that you can use U substitution here just as much. The one we're actually going to focus on the most is actually going to be number 3, which looks like it's U substitution, but it's not quite entirely that way. So, what we have before is we had our powers, right? Say something like this, 1 over our x squared for our integral, right? So, if we do this, typically, we rewrite this as x to the negative second, and then we do our integral, we get x to the negative first, right? Divided by our new exponent negative 1, right? Okay. This is where this falls apart, is with our very first 2, 1 and 2. You're starting at negative 1, which of course, when we bring in a new exponent, that's going to be x to the 0 divided by 0. X to the 0 is not a big deal. That's just 1. But we can't have 1 over 0, can we? Herein lies the issue with the power rule, right? So this is where the derivative of natural logs come into play. Now, we could show a proof for all this, but I think you guys are going to just take my word for it. I think this time around, I don't think you really want me to start doing calculus proofs on the board. You guys didn't seem, if memory recalls, you guys weren't big fans of proofs back in Math 2. I don't think you're going to be fans of them now in calculus. Okay. See a lot of shaking of heads and a lot of eyes widened when I talked about proofs. So we'll leave that sleeping beast lie. So this is where we use this rule the most, is of course for these types of problems. Now, for number 3 stands out the most. Number 3 is looking at a fraction, looking at a rational expression, and if the numerator is actually the first derivative of the denominator. Something that would look like, say, if I have x squared here, this would then be 2x, right? If I have something like this, but in a more complicated setting, you can quick integral this to the natural log of x squared. This is using the chain rule we talked about for natural logs, just in reverse, right? We just did this just a moment ago where I said, okay, the derivative of it's going to be 1 over what's inside, right? Where I get my x squared, and then times the derivative of what's on the outside of this, which would be 2x, right? So you see how this chain rule applies in reverse to create this integral, right? So this is just using it in the opposite direction now to get back to the natural log. This one is probably the most useful of all the rules we'll talk about with these natural logs. I will also say that it is the one that is probably the most difficult to use. It's the one that we'll try to use the most often, and it's the one we're going to try to create. It can be hard to see from time to time when it's not something easy like this one here. Okay? Are we all set here with slide 3 with the basic understanding of where these rules came from, why they're good, and what we're going to do with them? Okay, let's go on then to slide 4, and let's do a problem. What do you think the integral here will be for slide 4? Go ahead, do it. It should take you all of like 30 seconds, I think. Okay, and who is ready to help? Because we should be just about done. Miss Grice. Miss Grice, what did you do to attack this problem?
So, 2 is u prime, and then the x is u, so it's just equals natural log of 2x, right?
Not quite. Overcomplicated. Dawson?
Wouldn't you just take out the 2?
I'm going to take the 2 out like a constant multiplier. Yes, sir. Then what?
Have your 1 over x,
Which is the rule flat out, which is going to be natural log x, right? Plus c. Let's not forget that. We're not doing these as set integrals, right? Okay, only other thing we'd want to do here with this 2, sir? We could bring it up, make it natural log of x squared, right, plus c. Questions here or concerns here about this one? Awesome. John? Power rule brings that up. Okay, let's move on then. Next slide. What is it, slide 5 now, I believe? Keep a track. You never know. Yep, slide 5. Let's try this one out. I'd like to fire through these first couple ones relatively quickly so that way we can move on to some of the more complex ones. Who wants to help us out here? Miss Grice, you want a shot at redemption here? I'll help you out.
Okay.
Yeah? So, this does not just convert easily over to natural log of 2x minus 1. That's not how that works. Okay? This is why I said we're going to use u prime as our primary rule. Okay, so let's take a look at the work that I have here. First thing I'm going to do is set u equal to 2x minus 1, right? So if u is 2x minus 1, Allie, what does that make du, or u prime? 2. Okay? So what do I need to bring in to make this u derivative over u? I need to bring in a multiplier of 2, which means outside I'll have a 1/2. So this becomes 2 over 2x minus 1 dx, right? Or if we want to use our u substitution, use derivative over u which now we can convert to that natural log u plus c. Are we okay with the steps we've taken here? Only thing we want to do, Allie, is we do want to get back to x, right? Correct? And of course, we could bring this 1/2 up and make it our exponent, which of course we would leave it as 1/2. We'd convert that over to our root. So let's double check our work here on our slides. The first thing we said was u is going to be 2x minus 1. That makes du 2 dx. So we just did our u substitution. Now you can either write this in this format of u prime over u dx, or you could write it as just 1 over u du. Either one is okay. So I'm going to put a little caveat here, or 1/2 1 over u du. So just pay attention to how you're setting this up. If you're going to use dx, you're going to put u prime here. If you're going to use du, then it's just 1 over u. Are we all okay so far? Solved this down, brought it back, made it into a root. Issues. You see why I said this is going to be the one we're going to use most of the time, right? The only time that we're really going to use the traditional 1 over x is the natural log x, is if that's all we have in the denominator, is just a standard x, which is not going to happen very often. Most of the time, we're going to have at least a linear setup down there. Okay, let's move on to our next slide, which is not legible at all. It was on my screen, and it is not now. Okay, so let's fix that, because I can't even read what that says. Bounded between some stuff, that's all I can tell you it says. Okay, now it's perfectly legible here. Oh, my goodness. Technology, gang. Can't live with it. Most certainly can't live without it. First, let's move that over. Maybe we can switch this to like a different font here. Maybe that'll make it more clear. Let's make it Arial, because most certainly should be able to read it that way. All right, let's pick this up here. That's way better. Way, way better. Okay, so slide 6. Kind of a little bit goofy, a little bit messed up, but now that we have it fixed, let's see if we can set up this problem here. Who wants to help me just start by setting it up? I know this stuff's already popped up, but I think we can figure it out. Allie, why don't you pick somebody? Somebody I haven't heard from today. You say John? Okay, John, read out our problem for us there, sir.
Find the area bounded between the x-axis and the graph y equals x over x squared plus 1 and the line x equals 3.
Okay, so what are we talking about here?
We're trying to find the area.
Yep, so what are we going to use here? We're going to use an integral, we're going to use a derivative. What am I asking for here?
Integral.
This is an integral. Integrals find area, right? What's our parameters here for this? We have our function very clearly, right? So I know that I have the integral of this function x over x squared plus 1, right? Dx, okay? It does give us some set points here. What's our interval for this? Intervals have a starting and a stopping point. So 3 is one of them, yes, but what's the other one?
I don't know.
Yes, you do. Between what and what?
X over x squared.
No, that's our function. Zero. Zero. You know how I know it's 0? Because natural logs can't be negative. Logs can't go past the y-axis. Logs can't go past the y-axis. And that's what we're dealing with here today. Right? So, let's set it up and let's solve it down. 0 to 3. 0 to 3. John, what are we going to do?
We're gonna find the derivative.
Yep. How are we going to do that? How are we going to find the antiderivative here?
Use substitution.
U sub, all right. What are we going to say? U equal to?
X squared plus 1.
Okay, if U is going to be x squared plus 1, what does that make du? Or u prime?
2x.
2x. Okay, so what do we need to do to make U substitution fully possible here? What multiply?
Oh, 2.
2. And what's going to go outside?
1 over 2.
1 over 2. 2x, x squared plus 1 dx. Okay. How do you want to write this in sets of U? How do you want to write this with U?
Oh.
I know it's going to be 1/2. I know it's going to be an integral. I know this is going to be U. Do you want to use U prime and dx or just du? Okay? It doesn't really make a difference. It's just purely notational. Okay? One last thing I should ask you is, do you want to keep 0 and 3 or do you want to switch those over to U interval? 0 and 3 were for x. We're no longer dealing with x. We have U. You can either switch it back to x later, or we could just plug these in and get values for U instead. Okay, so that would be 1 to 10. When I plug 0 in, I get 0 squared plus 1, which is of course 1. 3 squared going in, that gives us 10, right? Are we okay? All set with what John has done. Okay, let's do the integral, sir. What are we looking at here? 1/2 times what?
So I convert to natural log now.
Yep. Okay. You said natural log what?
X squared plus 1.
No, you told me that we're switching over to U and we're to stay in U.
Oh, okay. So natural log u.
Natural log of U, absolute value of U. Between 1 to 10. You want to leave the 1/2 out or put it in?
Put it in.
Okay? I'm going to put it in, we're going to make it in the square root. This becomes natural log of square root U 1 to 10, which is natural log square root 10 minus natural log square root 1. Are we okay? All comfortable so far? Okay, John, there's a couple of ways we can continue to simplify. What do you want to do? I can't subtract them. Not really. I can use the quotient rule because they're both logs, so I can use the log quotient rule. I can do some simplifying. What do you want to do? Okay. Root 10 doesn't simplify. Root 1 is
1.
okay. Natural log square root 10. Natural log 1. There's 2 steps that we can continue to do. Either one works. One of them is easier than the other. Hey, you got to know, not me. You should know your natural log rules. It's calculus. I'm not teaching them to you. Quotient rule, all right. It's a long way it'll be. Natural log root 10 over 1 which is
10.
natural log root 10. We made it there eventually. Sir, natural log of 1 is 0. Natural log of 1 is 0. Questions? Now, John went a little bit different way than what I did on the board. Let's see what I did on the board here. So on the board, started out the same way, of course. Set u equal to those things. I went with the u du notation. Not a big difference here at this point. But rather than going 1 to 10, I kept it 0 to 3. So that way, when I did my logarithm, I got back to the natural log of square roots of x squared plus 1. Is everybody okay with what I've done on the board so far? Of course, at that point, I just plug everything in the same way that he did. And I'm still going to get natural log root 10. Except for I did all my work a lot faster with a lot less steps in pink. Because once I got to this point, I know that that's just minus 0. Questions? Issues, concerns, any part of this that we're not clear about? Okay. Are we ready to move on? It will be painfully obvious to me if you're using things that you probably shouldn't be using to help you solve these types of problems, by the way. Because if you are, it's going to look an awful lot like John's work right here. It's going to use an awful lot like John's work right here, because that's how a computer would do it, is get it all the way down to this point. Most of them don't recognize and don't see this as equal to 0. Natural logs and most of those things don't work very well together in the first place, mind you. Logs and computers don't always mix. Okay, how to recognize this u prime over u set. So this can be difficult to do. It's been part of what has slowed us up the most. As we do this, this can be challenged. This can be difficult. Sometimes it's not possible to do at all from where I give you to start. If that is the situation, where you have a rational expression and you're not able to use the u substitution on it, then you will have to divide the rational expression. If you cannot use u substitution on it from the very beginning, you will then probably need to divide the rational expression. Now, we've done bringing in the multipliers and coefficients to help us with this situation. That's what we've done with the first couple of problems there. But what we're going to talk about on our next slide, which I believe is slide 8, is how these can start to look a little bit more complex. So, let's take a look at slide 8. I got 2 of them here for you. I got 2 of them here for you for slide 8. Let's see how far we can get. I'm tired of standing up here waiting for us to solve problems. Let's try these 2 on our own. Go ahead and get after it. Okay, who's ready to help out? Tom and Brian. Gentlemen, who's going to do which one?
I got the top one.
Brian, get the bottom one? Guess so? Okay. Tom, what'd you do?
Okay, well, at first, I was setting up my whole U substitution thing, right? So like I wrote like the U.
Yep, I think that's good. That's what I want to see. U is going to be x cubed plus x, right? That makes this 3x squared plus 1, correct?
Yeah.
Okay?
Okay, so then you have the thing where it's like 1 over U times du. Right? Yeah.
Absolutely. Absolutely. Which converts over easily?
The 3x squared plus 1 over x to the third plus x.
This would be natural log of u, right, plus c.
Yeah.
So this could be natural log of,
X cubed plus x.
okay, so we need to work on some notational things here. First off, Dom, that's an absolute value.
Yeah.
Okay? Second of all, we need to have plus c. Okay? Make sure that we're putting those things. Mr. Carlson, let's wake up there. Same nap time. Okay, move on to the next one. Right, he helps out.
I said secant squared x as the u derivative.
Oh, I think we might, well, as a u derivative, so that makes u
Tan x.
tangent of x, okay?
And that gives, with the u derivative over u dx is natural log of absolute value tan x plus c.
Natural log derivative of tangent of x plus c. Absolutely. Absolutely. Questions here about these two? You don't put the absolute value signs, you're going to lose points. You don't put the plus c, you're going to lose points. They're minute features, but they need to be there. If you don't put them there, then it's wrong. Especially for problems like this, tangent and this rational. Oh, I have that as 1 over, it's not 1 over. Both of these can and would spit out negative numbers if you let them. You cannot do the natural log of a negative number. It's one of the basic properties of logarithms. We talked about it just a little bit ago with John's problem. Therefore, you have to make sure that you restrict this properly. And the best way for us to do that is to set this with an absolute value. It is necessary. It is critical. You must do it that way. Are we all clear? Okay. Find me the integral. Next line. Find me the integral here. Gonna have to be creative on this one, gang. Play around with it. Yep. There's an easy way and an even easier way to do this one. I have to be candid. I purposely made a mistake on my slides here to see if we're actually trying the problems or if we're just following my work, copying my work down. Let's do this problem. Let's do this problem. You guys are gonna be mad at me. Okay. Who here is ready to see how they overcomplicated what is a very easy problem? What did we try first? What is the first thing that we tried? What's the first thing that we tried? Bringing in 1/2 and a 2. Why are we doing that? Caleb, I saw your hand come up. What did you try first? Why is Allie bringing in 1/2 and 2?
I thought you should. I tried to do that, but it didn't work. So I take the x out of the bottom, you can simplify it.
Yep. We're done. We're done. Yeah, if you try to do the 2 thing, here's what happens. Is when you send that 2 through, you have 2x plus 2 over x squared plus x, which is not the derivative. So you cannot do this. This does not work. What is on this slide is not correct. Purposefully not correct, to see if we actually are paying attention and trying to, or if we're just copying down my work blindly. That doesn't work. 2x plus 2 is not the derivative of x squared plus x. You cannot do that substitution like that. There's an easier way, Caleb's way. Rather than focusing on that, let's focus on the function at hand. I can factor out an x out of the bottom. Awesome. Becomes x plus 1 over x times x plus 1. Cancel your x plus 1's groups. 1 over x. Natural log x. So that leads us to our next slide. That leads me to my next slide, which is a very important slide for you, and is one that's probably going to frustrate you here in a minute. Is in slide 10. What do we do when use substitution does not work? Like on this last problem. What do we do? We're going to go with what Caleb did. We are going to find a way to divide these fractions. And that's what you did. You factored and you divided down. You divided out, you crossed out those x plus 1 groups. The problem here being is that's not always going to be the case. It's not always going to factor and cross out so easily for us. This might require synthetic and long division. Now, we did review synthetic division not that long ago, so I'm not going to be that hyper concerned about it. Some of us are looking at me wide-eyed like we've already forgotten how to do synthetic division. That's not great. We might use grouping, factor by grouping, to help us out here too. The goal, inevitably, is to divide this integral down, hopefully to something that we can, in fact, use u and u substitution for. Which is what Caleb and I did in a very simplistic manner. We divided down our x plus 1 groups out. We canceled them out. We canceled them out through division. And this is our u substitution right here. U is equal to x. Du would be 1 dx, which is what we already have. Questions here? Guys ready to try one of these? Now that I've outlined what we're going to need to do when u substitution does not work. Okay? Let's try this one. Let's try this. Someone's help me get started. Let's help us get started. Yep, no volunteers. Cool. Caleb, pick somebody I haven't heard from today. Those people would be the short list of Anne-Marie, Parker, Dawson, and Michaela and Todd. Those are the 5 I have not yet heard from. I've heard from Mr. Guida, Ms. Grice, Mr. Hada, and Ms. Beck. Todd, we need to divide these. How are we going to do so? Yeah, we're going to use long division. Can't use synthetic here because it's not a linear expression. Going to need to use long. How do we do it? You remember? Not precisely. Okay, well, let's see if we can help you out here a little bit. First, let's write it out. Okay, so I'm gonna do my work over here, a little side work over here. So we got our long division set up. We got our divider, x plus, we have 0 x's plus 1. Okay, we need to write it out 1 for each term. Okay? And then inside what we're going to divide with our x squared plus x plus 1. Okay? How many times what do I want to multiply this by? Let's focus on the leading terms here. If I want to multiply this by something to make these cancel, when I add and subtract, what am I going to bring in? Not just 1. We're going to subtract. I guess you could think about it as a -1 is what I was trying to drive at. 1's fine. 1's fine. Okay? We'll multiply everything by 1s. We got 0 x's still. We got a plus 1 there, right? We're going to subtract everything down, correct? Okay, so I've got 0 here. I've got x. I've got 0, right? Are we all okay with what we've done so far? Now, Todd, there's not going to be anything that I guess in theory, I could multiply this by another set. I could continue this out to keep going. I could multiply by like a 1 over x, right? If I multiply by 1 over x, that would bring my x squared down to a singular x term, right? And allow me to continue out, right? So first, let's go ahead, let's get the 1 up there, right? And then I divided, okay, and I got this x. Or we can just use that as our remainder, okay? Ultimately, what's going to happen, Todd, here is we're going to continue to get remainders as we go out, okay? This doesn't divide evenly. It doesn't divide cleanly. So let's go ahead and let's just treat this as our remainders. So we're going to have 1 plus, we have x over x squared plus 1. That's what our long division has come out to be, correct? We couldn't get rid of that middle x, but we could get rid of the x squared and the 1. Are we okay with this so far? We're all okay? All right, Todd, let's bring that back to our integral. 1 plus x over x squared plus 1 dx. Okay? Can you do this one? Can we do this integral here? Does that look a little bit better for us to set up with u and u substitution? Well, making it one fraction is going to bring us back to where we were at. That ain't going to help us. How about we split this integral into 2 parts? Let's split it over this addition sign. So we'll have the integral of 1 dx plus the integral x over x squared plus 1 dx. Yeah, we can use u substitution now on this one right here, right? So u would be x squared plus 1, which makes u prime 2x. So we are going to need a constant multiplier here, right? So we need to bring in a 1/2 and a 2 for this one, correct? So this becomes natural log of 1/2 natural log 1 over u du, which is going to give us, correct? That's all for the second part. Yeah? Okay? What's the integral of 1? No, don't overcomplicate. What's the integral of 1? Just x. Okay? Todd, let's finish it out. Let's do a little bit of simplifying here. Let's bring this 1/2 up, and let's get back to our x's, okay? Because we don't want to mix x and u together, so let's do both in the same breath here. So we're going to have x plus natural log. We're going to have our square root, our plus c. What's going inside our square root, sir? What was u in the first place? Okay, so x squared plus 1 going back. Let's see how we did. Let's see how we did. Let's continue on from slide 11 on to slide 12. Let's see how we did. So, picking up this integral, we did our u substitution. We did bring in the 1/2 and the 2 multipliers. I converted that over to the natural log of x squared plus 1, the absolute value of that, and I brought that to our square root. I don't have to specify that a square root is positive through the absolute value. We always take the principal root anyway, unless we're specifically told we need the negative versions of those roots. Questions here? Okay, so the other function of natural logs is to help us do some integrals that you might not have realized that you could not do until today. I'm giving you some integral rules for trig functions, but not all of them. And this is something that students at home online are just going to have to deal with for a moment. See, these are the ones that you knew prior to. These are the ones we talked about in Unit 4. This is on 4.1 that I gave you some basic trig antiderivatives, which were just your trig derivative rules in reverse. That's what we talked about on this slide, if you remember that. Vaguely, hopefully. What I want you to notice here is when you look at these rules, the integrals don't have basic trig functions. We have sine and cosine, the integrals for those, but the next 4 are secant squared, cosecant squared, secant, tangent, cosecant, cotangent. Up until now, you were not able to do the integral of just tangent. You were not able to do the integral of just cotangent, or of secant, or of just cosecant. You had to bring in a second. We had to make this rule happen. So what these natural logs and what this is going to help us do is do the integral of just tangent, just cotangent, just secant. So that's what you see here. The top two I have not changed. The integral of sine is negative cosine. The integral of cosine is positive sine. Those two have not changed. They are the same as they were back in Unit 4. Below that is how we will do the other basic trig functions. Rather than looking at secant squared, just secant. Rather than looking at cotangent, cosecant, just looking at cotangent, just looking at cosecant. You all get to be lucky here, and you don't have to memorize these. You don't have to memorize these. Check out time frame here. We've got about 10, 15 minutes. We'll see how far we can get here. See how far we can get. So, doing problems that involve these absolutely can be a challenge. Especially when I mix this type of stuff, like Todd and I just did, with that stuff over there. And as you can see down at the bottom, I went ahead and threw you a little bit of a friendly reminder of your Pythagorean identities, that sine squared plus cosine squared would be tangent squared, or things like that. Things that you might be able to might want to use as you're looking at these. The reason why I'm bothering to point some of this out, of course, is if you can get tangent squared plus 1 inside your integral, then you can convert that over to secant squared, which goes back to 4, which is an easier integral to do and doesn't require natural logs. Same thing with the one above it. 1 plus cotangent squared is cosecant squared. If I can get that, I can go back to cosecant squared and go back to what we did at 4.1. Which doesn't involve having to do natural logs. That's why I put these up here as gentle reminders for you. You guys want to try one of these problems? It's not really a question. I'm more telling you that we're going to try one of these problems, but I'm more asking, does anybody want to be the guinea pig? Michaela's going to step up to it. Okay. Okay, let's do this problem together. This is slide 14. I think it's the last slide on my lesson here today. When we finish it, I'm going to cut you loose and let you just tackle the rest of these in your help. So we have the integral from 0 to pi over 4 of the square root 1 plus tangent squared x dx. Okay. What do you want to do first? It is one of the theorems I just gave you. So let's use it. Which one is it? Okay, so we're going to go ahead, we're going to swap this for its counterpart, which is square root secant squared x dx. Okay, now what? Pardon? That's not going to help me. I haven't done the integral yet. Okay, let's not overcomplicate. I got something squared, I got a root. What's going to happen? They cancel. 0 to pi over 4 of secant x dx. This is why I reminded you of those Pythagorean identities. Typically, if you're going to use them, they are going to be pre-integral. and they can help you make what is otherwise a very difficult problem into a much more simplified one. Let's check our steps here so far, Mikhail. The first step looks good, swap. Next step looks good, reduce, okay? You take good notes. I know you take good notes. What's the integral of secant of x? It's on the last slide. You have slides open right here, right? Okay, let's just go back a slide. Okay. Natural log of secant plus tangent, right? So we got the natural log, the absolute value, secant x plus tangent x. Everybody okay so far? Okay, Michaela? Now we'll plug it. Let's go ahead. Let's do that. Let's do that with pink here. So let's put in our 5/4s. Let's put in our zeros, right? So natural log secant 5/4 plus tangent 5/4 minus natural log absolute value secant 0 minus tangent 0. Okay. Are you ready? That didn't sound like a very confident yeah. Okay. Okay, so let's start with what is, let's start with secant. Secant is 1 over cosine, right? Okay, so we're just going to flip our cosine function there. So this one's going to be natural log of 2 over root 2, right? Tangent of pi/4 is 1 minus, what's cosine at 0? That's 1, right? So we're looking at natural log of 1 minus 0, which is sine over cosine, right? Are we all okay so far with some of our work? Okay, how many more steps do I need to show here? No, like how much more work do you guys want me to show to finish out this problem? Should I skip a few steps, or do you want me to show every little detail? How confused are we right now?
Show everything.
Show everything down? Okay. So, Miguel, the next thing we're going to do here is we're going to reduce these interiors of these natural logs, right? Okay, so I'm going to carry my work over because I'm out of space here. Let's just recopy up here. So I got natural log. I'm going to convert this to 2 roots. Okay, so 2 over root 2 minus root 2 over root 2 minus natural log of absolute value of 1, right? Okay, now this part is going to become what again? We did this earlier. This becomes 0, so this whole thing goes away. All right, let's focus on this part. Natural log of 2 minus root 2 all over root 2. Okay, so far so good. Okay, let's rationalize because we don't like it that way. Natural log 2 root 2 minus 2 all over 2. Multiply the top and bottom by root 2, right? Okay, I'm going to factor out a 2. of everything. Cancel those, right? And I'm okay with leaving it right here. I don't know why it says X, it should say 2, that's just my fault there. And I have that as a minus, I think that should be plus. Mr. Calvin has a couple of typos there on his slide there. Questions? If you want, you can keep going. If you want, you can keep going. You can actually get a decimal here for this. Square root 2 is like 1.41, whatever, so we'd be punching that in directly into the natural log, and it is going to give you some decimal answer back. Or you can leave it just like this. I would take this as a good answer here for us right here. Questions, issues, concerns about this one? Technically, there's 2 answers here. Because we could go with the positive version of root 2, which once again, as I said, is 1.4 something, right? Minus 1, so we would do the natural log of 0.4. The alternative is to do the natural log of the negative root 2. So we have negative 1.4 minus another 1, which gives us negative 2.4. But because it's an absolute value there, it actually be the absolute natural log of positive. And technically, there's 2 different answers here. Questions here, concerns here. Now, the reason why we want to consider the second answer with the 2.4, the natural log of 2.4, is because that one's outside of our interval. That's outside the interval. We're only running pi over 4, and that one's too big. So while there is technically 2 mathematical answers to finishing this out, where you can do a plus root and a minus root here, the plus version giving us natural log of like 0.4, and the other one going with the negative natural log of 2.4. This one is too big, it doesn't fit the original interval given. Are we all okay with why, how we're finishing that out, what my thought process is there? Questions? Concerns, issues, meltdowns? Were we feeling good all the way up until like the last 2 problems? Todd's problem and Michaela's problem. Todd's wasn't too bad. We just need to use a little division, a little math 3 skill. Michaela's is a little bit rough, admittedly. Okay, this is it for today. This is all I got. So, this was on live stream. I guess I'll see us all later. And the rest of you can go ahead and start your homework. Got a few minutes. Suggest you go ahead and get started.